So let's look at an example of this. And for that example, we need a certain corollary of the theorem. The theorem meaning the theorem of the section. So to the special case where we are going to deal with surfaces sitting inside R3. So it's a two surface sitting inside R3. So if you have a geodesic which has non-vanishing um, velocity vector field, so nowhere vanishing velocity vector field, then so what is it that I want to say? I want to say when something is parallel and tangent and so on. So then whatever is given by the theorem, so a smooth vector field. So what the theorem tells us? So smooth, there is a smooth vector field which is parallel and is tangent to the surface. So tangent to the surface along the curve is parallel along the curve if and only if both the length and the angle between the vector and the velocity vector of the curve are constant along the curve. So this is the angle between x, the given vector field, and the velocity vector field, constant, r constant along the curve gamma. So I will skip the proof for now. So it still is very useful, interesting proof to do, simply because you pretty much use all the properties of covariant derivative along curves that you had. So I'll simply write. So you just have to refer to what properties you know. It's very suggestive because we already proved, okay, so lengths and angles are all same. The interesting part in the proof is also to show that x is parallel, right? So assuming that is probably the interesting direction, right? So it's an if and only if statement. So saying the angle and the lengths are constant and showing that it is parallel is probably the interesting direction. So let me so it's actually an interesting proof, but so let me skip that for now, um, and do the example that is illustrative of this notion of parallel transport. So what you do is we consider the two-dimensional sphere. So of course the two-dimensional sphere is parameterized by two angles. Yeah? So you take one and with respect to that define curve. So 0 pi. So typically I get semicircles here to S2. So given by Um, so what is gamma theta at t? So this is your usual parameterization for the two sphere. So cos theta sin t, sin theta sin t, I don't have space, and cos t. So where does it go from? So t is 0 will mean the north pole. So 0, 0, 1 um, is parameterized curve joining the north pole and the south pole. Okay. So the exercise here is can we write down parallel transport? So in particular, if you want to define parallel transport, we need to find that unit vector field which does the job for us, which at a defined on some 0 pi here, which at 0 will give you um, north pole, but also a given tangent vector. Yeah. So at p, so between okay, so n and so this is then 1, 0, 0 be something in t p s2. So it's a point and the vector now r3. Now by the so you're given this, we're given point. So by the so without directly applying the theorem, it is useful to apply the corollary here, right? So vector field is tangent to s2 along the curve, which is tangent to s2 along the curve will be parallel if and only if it has constant length and makes constant angle with the curve gamma theta. So so this is what we will so by the what they write it as corollary. So by the corollary above along the curve if and only if it has constant lengths and makes constant angle with the velocity vector field of the curve. So towards this define, so the point is of course to figure out such a vector field. So this I define to be cos theta. mm, minus sine theta. So this is what should be the term? Normal here, no? So sine theta. So normal gamma theta at t. Mm, maybe I should write this on the next line. But this is normal, so I want to remain on the plane. So I take the cross product with the acceleration. Sorry, no, what I'm saying with the velocity vector field. So you land up in the tangent plane itself. So here, of course, n is the orientation. Yeah. So yeah. So the plus one here. So this is the outward. That's just a choice, of course, of sign. And now we can define the parallel transport. P gamma theta of V is this V theta at pi. So you can just write out what this is. So this is cos theta. So that no need for a bracket here. So this is cos theta. Calculate this. So this is, of course, at pi you get Q. So Q minus cos theta minus sin theta 0 minus so sin theta 0, of course, sorry. So I forgot one coordinate. So this will come up to from old trigonometric formula. So picture is very useful here. So this indicates the various possible parallel transports from the north pole to the south pole. When you change theta, of course, you get different uh, semicircles. Of course, note that we want uh, geodesics and the curves we have, because the parameter only ranges from 0 to pi. What this will give you is it will give you one semicircle between the north pole and the south pole. If you change the angle, you get different semicircles. Yeah? So, and along which you move from one tangent space to the other. So that is to note that it's very much dependent on the path, right? So if you choose a parallel transport between the same points with the same initial vector, but if you take different curves between them, then the corresponding parallel transport need not be the same. Of course, you can replace this smooth curve by piecewise smooth, as you can imagine, right? So you just go from to all the intermediate vertices with small segments like this, and traverse from P to Q. Smooth curves by piecewise smooth. The So there you simply go from the initial point to some intermediate point, from that intermediate point to the uh, other intermediate point. So at every stage, of course, it takes you some vector to another vector in that tangent space, and so on and so forth. So just going one after the other, you go get a um, parallel transport from the original point, starting point, to the ending point. So the interesting point about this is also the first instance of something we will see is an isometry. So with notation as above, so that I don't have to write everything again. So with notation as above, um, P gamma from, so I'll simply say between 2 points. So TPS to TQS, um, is a surjective linear isometry. So, what does the surjective linear isometry mean? First, that it is linear, surjective. So, linear and surjective will, by rank nullity, give you injective as well. So, it's a linear isomorphism, and it's also an isometry. In that, it preserves inner products. So, what is isometry alone? I will write out. So, what is linear isometry? So, what is isometry? It happens to be linear in this case. So, isometry is the inner product from P gamma between some vector and some other vector is the same as the inner product between the vectors u and v themselves for everything in the tangent space at P. So okay, this is immediate. So let me just remark, linear and so on is completely clear, right? So there's nothing to show. um, the other thing is now to notice that, um, so linearity, what do you have to use? You have to just use that covariant derivative along a curve, preserved sums and commuted with addition of vector fields and scalar multiplication. So that, in other words, it respected the underlying linear structure, so it's a linear map. So um, okay, so surjective, but surjective is easy because so first show isometry. Isometry means it's injective, and by rank nullity it was also surjective, right? So let me only write that. So if you show isometry first, the gamma is shown to be a linear isometry. Um, then P gamma is injective, right? So isometry is obviously injective maps, and so by rank nullity is surjective. So that's why linearity is useful. Yeah. So how does one show? Therefore, the only thing which is to show that it is that it's an isometry, but that also is really a consequence of the fact that because what is this parallel transport? You go to the inner product. So this P gamma u is going to be some capital V at some point B, and at some other point, and so some other vector at that point. So what this will give you is, what do we know about pairings of, because those vector fields that we get, that we use for parallel transport, so these are parallel vector fields, and so for parallel vector fields, we saw that their inner product is constant. Yeah, so this I think we mentioned somewhere. So parallel along curve. Yeah. So the point two here, right? Properties of Levi-Chita parallelism. Property two is if you have two parallel vector fields along a curve, then the inner product is constant along the curve. So that's what you use for isometry here, because the vector fields that you get in defining parallel transport, those two, one corresponding to u and the other corresponding to v, those two are parallel vector fields, and therefore their inner products are constant. Yeah, so it's this meaning that in particular their values at arbitrary points are the same as the values at the initial point. And initial point is u comma v. Um, the other endpoint is p gamma u and p gamma v, but they all are the same. So that is this. So that's also an example of what is called an isometry. Yeah. So two things which we should have in mind from today. One is the speculation whether covariant derivative along curve is so, because by its very definition it only sees what happens on the surface and not how S sits inside. It's intrinsic, so that would be a good guess. And the other is, of course, that these parallel transports are being isometries. Yeah, so the reason that isometries are important are because that's what it means to have the same geometry, right? So in group theory, the morphism there is homomorphism. You say, okay, two groups are isomorphic, so under group homomorphism, then they are essentially the same group. So as a group, there is no distinction between them. So in each, so just if you look at smooth manifolds, so if you look at topological spaces, then you have homeomorphisms. You have smooth manifolds, then you have diffeomorphisms, and the corresponding notion in the case of geometry is that of an isometry. Could be local, but is that of an isometry. So that preserves the metric. Yeah. So that's why it's important. So two manifolds which are isometric are the same from the point of view of geometry. Yeah, so I'll therefore transpose a little bit to that. I'll perhaps make some comments before I go there. Uh, so essentially our agenda in what remains of this and tomorrow is to see a little bit of flavor of what happens in the arbitrary setting, but always having the surface case in mind, hypersurface case in mind. And in particular, because there is something specific to our situation, because you do have an ambient space always. So that relation of the geometry which comes from the ambient space versus the quantities which are intrinsic to the space. So this discussion we will have. But I will make maybe a few preliminary remarks here concerning geodesics. Of course, these. What did I want to say? Yeah. So I think I did mention geodesically complete. So we said if so a geodesic is complete. So these are sort of remarks. So a geodesic is complete if it was defined for all time t. So the usual maximal geodesic is defined on some interval. This need not be all of R. But plenty of examples that we saw, it was all of R. For various reasons, we will see some why they are so. Is complete if it is the curve is defined on for all time t. If the geodesic is defined for so you call a space so M is your Riemannian manifold. I'll say what it is, but in our case, let's say slash our surface here, n surface. So this is the example we have in mind. Um, so it's geodesically complete if every geodesic through every point on the space is complete. Yeah. So that seems like a very strong statement, right? So even if something goes wrong at one point, you lose this. So this is what actually happens too, right? It's very easy to distort this. So you take maybe the R2, the plane. So we know what the geodesics are. These are straight lines or segments thereof. But so all these straight lines are infinite straight lines. So these are defined for all time. So this is fine. However, what happens if you look at the punctured plane? As I say, remove the origin. You take a straight line passing through the origin. The origin is no more in your space. So you simply lose geodesic completeness. Yeah? Because if you want to come around the origin, however small your curve is, you have to have some, you can't do it through a straight line, right? So you have to move around the origin in some way. So this is lost. So completeness is of course a subtle property in that sense. Yeah. So after all, even in the usual notion of topological completeness, compact spaces are complete topological spaces, say like even metric spaces. So look at the sphere. Uh, so you could remove a couple of points and everything would end. Yeah. So okay, so that is geodesic completeness. On the other hand, so for many things we need lengths of curves. So already we defined this, so by looking at the length functional. So recall that, so that given a curve, so L of gamma. So the length of a curve is on some interval wherever the curve is defined, a speed of the velocity vector field, right? So this required, so you take the curve, you take its velocity vector field, look at its speed, integrate over the interval over which it's defined. And of course, this norm is dependent on the existence of an inner product. Yeah. So I'll come to that in a bit. But suppose there is such an inner product on every tangent space, right? So after all, the parallel transport also suggested that, right? So what we could see was it's an isometry from, so in parallel transport, the isometry this here is the inner product on the tangent space at point Q. This is an inner product on the tangent space at point P. So they are actually even distinct spaces, and the claim is merely that they are the same as numbers, right? The left hand side and the right hand side really coincide as numbers. So, so ideally one would like to have inner products on tangent spaces, and that this varies smoothly as you change the points. Yeah. So So but anyway, so once you have an inner product, then you can have lengths of curves, as we saw. um, and so when they start saying this, okay, isometry, etc. But oh, geodesic completeness, right. You can define a distance function. So this is the interesting bit, um, between points on. So whenever you have a Riemannian manifold, so in other words, every tangent space has an inner product, like in our case of n surface, which varies smoothly. Um, we can do this. So what we can do is, so you look at 2 points. So let P comma Q be in M. Always think of S. Yeah. So I'm just writing M so that just to indicate that it may be. Is true in more general setting, like much of what we did, but it's not clear, right? Because many of our arguments constantly use the normal vector, right? For example, that the tangent acceleration is normal, etc., etc. So it, in some way, seemingly involved the ambient space. So it becomes important to distinguish between what is dependent, which geometric quantities are dependent on the ambient space and which are not. So, in fact, in the theory of hypersurfaces, it becomes the most important question. Okay, so you take 2 points. I will ask for connectedness here. So, I think it's important. So, as I mentioned, otherwise we simply looked at each connected component. We already had this discussion once. Yeah. So, if it's not connected, we simply look at each connected component separately, yes, as a distinct manifold and or a distinct surface. So again, M is connected here, so it's always going to be connected Riemannian. So you can define what is called the Riemannian distance. Perhaps I should have said this after the Riemannian metric, but it just struck me now that then I okay. Um, so between these 2 points, what you do is you look at all the curves joining P and Q and look at their lengths. So look at L of gamma, where gamma is smooth. I mean, I can allow piecewise smooth, I suppose. So gamma is piecewise smooth curve joining P and Q. So I look at all curves joining the 2 points. I look at their lengths, and then I look at their infimum. I call this the Riemannian distance. Of course, there is work to do. So what happens in, so for example, um, what is this, if you take Rn Euclidean space, right? You take 2 points, you look at all the curves joining them. So you already know the solution to that variational problem. The straight line segment is the one which has which is the shortest distance. So the minimum, the infimum is actually attained there. Yeah. So, and punctured plane example is an example where there is no shortest curve, right, joining these 2 points. So I mean, any 2 points, let's say on the opposite side. So 1 0 minus 1 0, something like this. Yeah. So um, right. So of course, we have already seen that geodesics are, so things which minimize the length functional are necessarily geodesics, but not every geodesic attains this infimum. So that is there. Okay, so once you have a distance, so with respect to this distance, the Riemannian distance, um, the manifold that you start out with is a metric space, right? After all, you have. Now, part of what is called Hopf-Raynaud theorem is that, so it says a few more things, but I'll only mention what, so 2 points here, maybe three, just to make a good analogy. Is if M is geodesically complete, if and only if MD is metrically complete, is complete as a metric space, because geodesic completeness is a tough one, right? So you have to say every geodesic for some reason is complete, while the metric completeness is an easy one. Yeah. So and, and the distance is also a nice distance here, right? So and this, in fact, you can also say is the same as closed bounded being compact. So Heine-Borel also holds, yeah. So closed and bounded subset of M is implies compact. For subsets of M. Yeah? So this is just a little bit of it puts together some of these things that you have seen. So lengths of curves in terms of geodesic, so geodesic completeness. So the infimum, because the distance itself is in terms of infimum of lengths of curves, and so curves which attain this are necessarily geodesics. Yeah. So and so completeness is metric completeness is the same as geodesic completeness, and Heine-Borel holds. It also says some more things, but we will. So this is an interesting and important result. Of course, this Riemann keeps coming up, as you might have seen. So much of the modern theory of geometry, in many ways, arose from him, in the sense that, so perhaps you have heard of this story, right? So both Gauss, so because the theory of surfaces as we see it, Gauss knew it. Yeah. Um, in fact, the notion of what is intrinsic and so on, this I will describe, is essentially what Gauss observed. Yeah? So the sort of the ultimate theorems, and something like Gauss-Bonnet as well. So relating geometry and topology. So pretty much what was there to know about surfaces, Gauss knew. And at the time that Gauss was in Göttingen, so was Riemann. Gauss was, of course, super established, world renowned. Riemann, not yet. And in those days in Germany, of course, in order to have the right to teach, right? So this does not mean you might have a salary, but in order to have the right to teach, you had to write up what was called a Habilitationsschrift. Yeah, so something after your PhD, you put together. So in those days, of course, it was taken very seriously, and so Riemann was. So it still is true that you give a list of topics on which you propose to write your habilitation schrift, and a committee chooses what you have to write. And so among the many things, I think. So among the many things, Riemann had proposed foundations of geometry as one of the topics. In fact, in his list, it was the last so what had, of course, Gauss saw this and he immediately thought, okay, who is this upstart who wants to talk of geometry? After all, I know what is there to know about it in some ways. And so Gauss asked him to write about it, and that is why we have Riemannian geometry today. So he actually wrote this up in a short span of time. And in fact, I once heard, I think it was V.S. Varadarajan, Indian mathematician. So in a talk mentioned that Gauss even talked about, Riemann even in his habilitation script talks about infinite dimensional manifolds, right? All these manifolds we talk of are typically finite dimensional, but even infinite dimensional ones are known is so it was due to Riemann. So that's why Riemannian keeps occurring a lot. And so okay, so what was that? That was just an aside. So we have to thank Gauss for the existence of Riemannian geometry. Let's look at isometries maybe and go on to see what is intrinsic means. Yeah. Um, so so okay. So what should be our setting? So we will sit inside our n surface contained in our Euclidean space. Um, uh, so maybe you take two of them because I want to compare. So SS tilde. Um, so so we want to first define what a local isometry is. So it is a smooth map from one to the other. Okay, so these sit inside. Okay, so you don't even have to have this. Okay, so I will leave it as such. So you don't have to be this strict about it either. But okay, so if so, it's anything local is typically something at the level of tangent spaces. So smooth map is a local isometry if it preserves inner products. So if it's derivative, in other words, if maybe I write the formula. So derivative of psi acting on some vector v, derivative of acting on some vector u. So this is the same as the inner product of u and v. So so one is, so here you have the inner product on the tangent space at some point in S tilde, here at some point in S, and so on. Yeah? So P in S and the image of that there. So this is for all vectors uv in the tangent space at P for S. So let's say map from S, right? So this is here T psi P S tilde. This is in the product on the tangent space at P of S. Sorry, of S. I wrote S tilde. And so once you have an isometry, right? So what can you say? So that it says that the differential is so same dimensional. Yeah. So after all, so you have by inverse function theorem that locally you have a diffeomorphism from one to the other, right? So, but as a map, fully it may or may not be. Yeah. So this is why you only have a condition on the derivatives. So it's going to only give you some conditions that are local on the manifolds. Yeah, on the surfaces. So, but if in addition, this is 1 1 on 2, then it's what is called an isometry. Yeah, so if in addition um, mm, psi is bijective, psi is called an isometry. And the question of when two n surfaces are the same is the same as asking whether they are isometric or not. So the correct notion of an isomorphism, when you consider smooth, Riemannian manifolds, is that of isometry. Yeah, so all these rigid motions that you might have seen, these are isometries. So I'm sort of running out of time. So let me okay. So let me say that. Tomorrow we will look at some quantities which are intrinsic. We'll see what it means to be intrinsic, and in view of what isometries are. Um, and then I maybe make some other general comments and stop. So for now, I will stop here.